Hey, Honors Geometry students, welcome back to second semester of Honors Geometry and your first lesson. This is so exciting. So in this video, what we are going to be doing is this objective hopefully looks somewhat familiar because this is what you had just done in class. So you're going to be using your knowledge of similarity, right triangles, and right triangle vocabulary to successfully define three trig ratios, right? And so we're going to begin to apply those three trig ratios that you learned in class. And so throughout this video, you're going to see some review and summary of what you did, as well as some extensions and preview of kind of where we're going with this. So hopefully you have your notes out or you have this presentation printed so that you are ready to follow along, and hopefully pause the video at different points so that you can try it and check your own understanding. All right, so I want to start off kind of like from the beginning. So I've got a map up here on the screen, and this is actually a map of DC, right? So maybe you've heard of it, maybe you've been, it's not too far, maybe you haven't, I don't know. So this is DC, and we've got some streets here, and so I want to make some connection here with some things that you do know. And so I already drew the triangle in. There's other places on here I could talk about too, but I want to focus in on these three streets. Okay, so I'm looking at K Street. This is what my directions tell me: Pennsylvania Avenue and 17th Street. The intersection of K Street and 17th Street forms a right angle, right? Those two streets are perpendicular to one another. So I'm going to go ahead and draw in the right angle symbol because I know that that's there and that's going to help me. So this is just a label. If you can kind of see, like, this is K Street. Ugh. This over here is 17th. I can look at those streets. And then this right here is Pennsylvania. Maybe you see some stuff over here. Oh, this looks familiar. Do you know who lives on Pennsylvania Avenue? If not, look it up. Okay. So what is K Street's relationship with angle C? So angle C, it's a little silly. Like, angle C is the intersection of K Street and Pennsylvania Avenue, right? And so what is the relationship between K Street and angle C? So like, I'm in DC and I'm standing right here at this corner. K Street is blank to where I'm standing. Oh, it's adjacent. What about the relationship of Pennsylvania Avenue to angle D? Right? So now I've walked, I've moved, and blah blah blah, and I'm over. I don't know why I said blah blah blah, but I'm over here now. Well, in relation to where I'm standing, what is Pennsylvania Avenue? Well, that's the street that doesn't change, right? That's across from my 90-degree angle. That's what we would refer to as the hypotenuse. That's the longest street. No matter where I'm standing, no matter what my perspective is, that is going to be the longest chunk of street that is formed by this intersection, by these three streets intersecting. What about Pennsylvania Avenue with C? So now I've gone back over here, or maybe I'm here and my friend is here. Well, Pennsylvania is still the hypotenuse, right? That doesn't change. Hypotenuse doesn't depend on perspective. It doesn't, right? That was something that we talked about actually at the end of first semester last week, right? That depends on, well, where is my right angle? Well, building on that then, what is, oh no, I can't see it. Can I do this? Oh, I'm going to move me. Darn. Let's see if I can do this more effectively, like this. No. Well, I can still see it. What is K Street's relationship to angle D? K Street to angle D. That's what question 4 says. So angle D is over here, so that's my person down here. K Street. Well, K Street in relation to C was adjacent, but now when I'm over here, I have to cross. It is opposite of where I'm standing, right? So you need to pay attention to which angle you're talking about. Is this reasonable? Explain your thinking. Yeah, right? The hypotenuse doesn't change. Hypotenuse does not, oh goodness, depend on perspective. It doesn't change. It is like, we had never said those words really opposite and adjacent. You've heard them. We never really said them in relation to a right triangle until the end of last week, right? But you were still able to identify the hypotenuse. So don't lose those things that you did know. Okay, so it's good. We want to be able to identify where, like, label the sides. We want to know, like, what is the relationship between an angle and a side? A reference angle is the term or the word that we're going to be using. So from class, let's take a moment and let's recall the 3 trig ratios that you guys learned about today or yesterday or the day before in class. You got them? Hopefully they were sine, cosine, and tangent. Oh, wow, I spelled tangent wrong. Oh, goodness. I'm going to change it. Oh, no. I'm going to change it during the video. And then I'm going to pretend like it didn't happen. There we go. Sine, cosine, and tangent, right? And they are trig ratios of right triangles. It is called right triangle trig, right triangles, right? And so when we're saying it's a ratio, that's why I keep saying the word ratio. Sine is the ratio of what? Opposite to hypotenuse. Cosine is the ratio of adjacent to hypotenuse. Tangent is the ratio of opposite to adjacent. If we don't have a right triangle, we will not use these. Like that is a question to look out for, right? If you're asked to identify the sign and you don't have a right triangle, then this isn't going to work. If you're asked to identify the sign and you don't have a picture at all, well, what picture might you draw? Maybe a right triangle, right? So to give you a visual, you saw an image just like this in class, right? So sine is abbreviated SIN, and these are buttons that you see on your calculator. Cosine is COS, tangent is TAN. Even when you're looking at this, like this is still sine, cosine, tangent, right? And so these are the abbreviations. Theta, it's a Greek letter, often used to represent an angle. Just like x, it's a variable. Is the reference angle. And so that's a good word to know. I guess that's 2 words. Reference angle. And so that's really like, that's where our person is. That's where our perspective is from. And so as you move theta to the other angle, right, your perspective is going to change. Well, what's not going to change? The hypotenuse, right? But what's opposite and what's adjacent, what's across and what's next to are going to change. Okay. So let's add some numbers into this. So I'm looking at this triangle ABC, and I'm asked to find some ratios. I'm asked to find the sine, the cosine, and the tangent. And right now on this slide, I've reminded you of what the ratios for the trig, right, for that trig function is. That won't always be the case. At some point, you'll know these, right? And it'll become second nature to you that, oh, sine, that's opposite of hypotenuse. You're going to be using this so much. It's like as much as you're going to be using the Pythagorean theorem. Always. It never goes away. So let's figure out, like, we can't really do this unless we know, like, where's our reference angle? Is it A? Is it B? Is it C? I know the sides. I know it's a right triangle, so I'm good to go. Well, A, B, C. Well, hopefully you remember that that middle letter is the vertex. A, B, C. So this is the angle. I'm going to stick a theta on there, actually. And that is going to be the angle we're talking about. Okay, I'm just finding a ratio. I'm not going to solve for theta. When I'm asking you for the sine of an angle, it's a fraction. It's a ratio. Okay, so the sine of theta. I'm going to label my sides. I like to start with the hypotenuse because that's the one that I knew before. It's across from the right angle. Here's my hypotenuse. That's H. And I like to do opposite. Let's say I'm over here. I'm looking straight across. This is the opposite. This is the adjacent, the other leg that forms this angle. Okay, just be careful with your handwriting and make sure your A and your H don't look the same. It happens. Okay, so opposite over hypotenuse. Well, this is almost like mindless to me now. I'm just writing it in. I labeled it 9 over 15. I think I'll go ahead and simplify. Right, they're both divisible by 3, so this is 3 over 5. I'm going to show you something pretty cool in a moment, which you probably saw in class, actually. Adjacent over hypotenuse. Well, that's 12 over 15. Let's simplify that. They're both divisible by 3 again. That's 4 over 5. Notice anything? And then opposite over adjacent is 9 over 12. And I can divide them both by 3, and that's 3 over 4. So watch this. I'm going to go ahead, and I'm going to kind of just put a line here. I'm going to approximate it. No, I don't like that. I'll stick it like right here. And I'm going to say, do you guys, hopefully you see this green triangle, and this takes you back to things that we did at the end of last semester with dilations and scale factor. And I'm going to say that I've now shrunk this, right, by a scale factor of 1/3. Ooh. Okay, so did I mean 1/3? Yeah, 1/3. So now this side length would be 4. This side length would be 3. Oh, these are going to be parallel. This picture should look familiar. And this green one is going to be 5. Okay, and I can ask you the same question. I can now say, so this is opposite, this is adjacent, and this is the hypotenuse of that little triangle. And I could say, hey guys, what's the opposite over the hypotenuse? And you would say, pretty crazy now, 3 over 5. Whoa. Right? They're similar triangles. So the sine of an angle, it doesn't matter if you've like blown the triangle up or you shrunk it. It doesn't matter if it undergoes that a dilation and the triangles are similar to each other, that ratio for sine, cosine, and tangent is going to be the same. We're not messing with the angle, right? In fact, I don't even need a triangle in front of me, and I can start asking you for sines of different angles. It doesn't matter how big or small the triangle is because everything is happening proportionally. So the ratio between the sides are the same. Even if I were to say 12 over 9 is the same thing as 4 over 3, right? We've been practicing those ratios. Now you're just taking it one step further, and you're going to be, we're eventually going to be solving triangles and solving for missing sides, which you know how to do, but I said sides plural, right? Like we've been stuck at this point where if we only had one side, we couldn't do anything. Trig is going to allow us to do that. So let's look at the same triangle, but what's different? I'm changing my perspective, right? I'm now over here. I'll call it alpha. Okay. In fact, you know, I could even simplify this triangle right away if I wanted. They're all divisible by a number. I could just simplify it right away. Pretty cool, right? I could see that there is a relationship. I could say, you know what, I think I'm going to divide them all by 3. And then I don't have to simplify later. Wouldn't that be kind of cool? Let's do that. 3, 4, 5. It's going to work out the same. I'll just simplify it up front. So in relation to now alpha, this is opposite. This is still the hypotenuse, and this is adjacent, right? So if I go back a slide, my opposite and adjacent have flipped. They've switched. So now the sine of ACB, opposite over hypotenuse, is going to be 4 over 5. Well, that's the same thing as what? This one, the cosine of ABC. Oh, sorry, too far. The cosine of ACB, adjacent over hypotenuse, is going to be 3 over 5. Well, that was the same thing that we got back here of the sine of this other angle. So the sine of this angle is the same thing as the cosine of this angle. Interesting. And then the tangent of ACB, opposite over adjacent, 4/3, right? Which isn't the same as anything else, but that's the reciprocal of the other angle, right? So some interesting things, like here's where I had theta, right? So the sine of alpha is the same thing as the cosine of theta. The cosine of alpha is the same thing as the sine of theta. The tangent of alpha, well, that was the reciprocal, so 1 over the tangent of theta. Right? So there's some pretty good relationships that you do here. Things that you use a lot. And these aren't things you have to memorize. I just want you to have exposure to them so that you're seeing it and you're starting to see these connections, right? What else is the relationship between angle C and angle B? If I told you that this was 20 degrees, what's this angle? Maybe you don't know, and that's okay, right? Maybe you're going to use the triangle sum theorem and you're going to say, okay, so 90 and 20 gives me 110. 180 minus 110 gives me 70. Okay, well, what was the relationship? 20 plus 70, well, that's 90. They are, what's that word? It starts with a C. Complementary. Right? So I could even stick these in the place of it. The sine of 20, oh, it's a degree. I'm bringing this in. This is different, equals to the cosine of 70. Hey, you know what? Why don't we look at that in a calculator? The sine, what did I say? The sine of 20. I'm going to go in my calculator. You guys, this is just Desmos calculator. The sine, there's that button, S-I-N, of 20. Am I in degrees? I think so. Degrees. I don't think I'm in degrees. I guess as long as I'm in the same one, I need to play around with that. So the sine of 20, keep that in mind, and then the cosine of 70. Did I change? There, now they're the same. I was not, oh, okay, now I am. So this is in degree, I was in the wrong mode. So you want it to make sure you can see the word DEG. We haven't learned about something called radians yet. Let's do it again. What if I gave you another one? Can that thing go away? And I said the cosine of 40. Okay, what should I put in the sine of to get the same thing? 50. Whoa, pretty cool, right? Pretty cool. Let's do a harder one. What about the cosine of 72? What should I put in? The sine of 18. They are complementary. They sum to 90 degrees. Really neat connections to make. So this looks a little busier, right? So let's see what this is asking me. I'm gonna name some of these angles. EDG. EDG. I'll call that beta. Okay, so it's asking me first for the cosine of beta. I need to focus in on the right triangle, right? It's right triangle trig. So I'm going to focus in on this triangle where beta is this angle down here. Cosine, do we remember it? You might need to go back and reference it. Cosine was adjacent over hypotenuse. Okay, so adjacent, now I haven't labeled them. The side that's next to this one, the leg, okay, that's 21 over the hypotenuse of this red triangle, 29. Oh, there's my answer. Okay, what about the sine of DGE? Now I'm talking about a different angle. This one up here, I'll call it alpha. The sine of alpha. This should be interesting. What's the relationship between beta and alpha? Alpha plus beta is going to equal to 90 degrees. So the cosine of beta, didn't we just figure out that's going to be the same thing as the sine of alpha? Let's see. Opposite over hypotenuse is the ratio. If you need to go back and reference your notes, use them right now. Opposite of alpha is 21 over 29, right? We just did this in the calculator too. What about here? What about this next one? the cosine of EFG. EFG, I'll call this theta. Cosine. So now I'm going to be focusing in on a different triangle here, right? Here's the right triangle that I'm looking at. Cosine is adjacent over hypotenuse. 21 over 29. So let's see. The cosine of these two angles, I got the same results. That must mean that these two angles are the same. Oh, theta must equal to beta. That's fun. Ooh, isn't this just an isosceles triangle? Oh my goodness, it's just an isosceles triangle. I don't know if it's a right triangle. I could figure it out, right? We could see, is 29 squared plus 29 squared the same thing as these two together? I can figure out if that's a right angle. I don't know if it is though. It's not, because these two sides aren't equal. If this 20 and 21, if these two sides were the same, then this would be a right angle, because then you would have like little isosceles triangles, but it's not. So let's see. Now this is a little different. Am I on pink? I am. Sine of GEF. Where's GEF? Weird, that's the right angle. Okay, so this is kind of like asking, what is the sine of 90 degrees? So sine is opposite over hypotenuse, and this is a little confusing, because what's opposite of the right angle? Well, 29. Well, what's the hypotenuse? Well, 29. So the sine is just 1? Are we allowed to do that? Are we allowed to double label it? Yeah, when our reference angle is at 90 degrees, absolutely. And let's show that let's see that in our calculators. Right, if I went in my calculator and I push sine of 90, oh, cool, I do get one, right? And that's one that you're going to be working with a lot as you move forward in this class and in math in general, that the sine of 90 degrees is 1. And it always is. It doesn't matter how big or small my triangle is, the sine of 90 degrees will always be 1. And that's why it works out like that. It's a ratio, right? It doesn't matter how big or small. And then the tangent of DEG, that's also a right angle. So tangent is opposite over adjacent. So what's opposite of this 90-degree angle? It's the hypotenuse. A little weird. Let's write it. What's adjacent? Uh-oh. Is it this or is it this? I don't know. I'm just going to stick a 0. I don't know. Well, what happens? What is 29 divided by 0? Undefined. You cannot do that. If you have 29 of something, you can't make 0 groups. That's impossible. You've got to have at least 1. You can't divide by 0. That's illegal. Right? Let's see what happens when I do that in my calculator. The tangent of 90 degrees. Undefined. How crazy. You can also see what the cosine is. Oh, it's 0. Let's see, it didn't ask me for that, but if it was the cosine of this angle, cosine is adjacent over hypotenuse. That's kind of like the I don't know in the numerator over 29 in the denominator. So that's like 0 over 29. Oh, which is 0. Right, so you just figured out what the sine of 90 degrees is, what the cosine of 90 degrees is, and what the tangent of 90 degrees is. You don't need a right triangle for it, but it relates to the right triangle. So now that we have those ratios down and we're able to identify them, what if we took the triangle away? Now it's gone. So we want to create triangles based on ratios. So here I'm given that the tangent of A is 3/4. Okay, A is not the right angle. So I'm going to sketch a triangle. Well, in not such surprising news, I hope, I'm going to sketch a right triangle. And I'm just going to go ahead and call this A and this B. And you know what? I'll call this C. The reason I'm calling these A and B are those are the ones that I'm asked about, and so those aren't going to be my right angles. Okay? So tangent. Well, tangent here, I need to know my ratios. Tangent is opposite over adjacent. So here's my reference angle. I'll stick a theta there. Opposite. Why isn't the A drawing? Okay, so it's close as it's going to go. is 3. Adjacent is 4. Well, how do I figure out that last side? Oh, our old friend, the Pythagorean theorem. It never goes away. 9 plus 16 equals AB squared. You guys know this. You might even know this one. We talked a little bit about Pythagorean triples last semester. When I take the square root, bam, 5 equals AB. And now I've got it. Now I have the picture that didn't exist there for me before. Right? I can now do the sine of A is 3/5. Sorry. I can do the cosine of A is 4/5. Okay, now I'm changing perspectives. I'm going to go over here to B. That's what it's telling me to do. The tangent of B, opposite over adjacent, is 4/3. The sine of B, opposite over hypotenuse, is 4/5. Remember this relationship. The sine of A and the cosine of, the cosine of A and the sine of B are the same. The sine of A and the cosine of B are the same. Adjacent over hypotenuse, 3/5. These, the tangents, the one that I started with and the one that I found here, are reciprocals. Don't worry about this. I'm not going to do that. I meant to delete that. You can, right? You can dilate it and give me another one. You can multiply this by 5 or 72 or whatever makes you smile. Let's try another one. This would be a really, really great place for you to pause the video if you have not done so already. So hopefully you started by drawing a right triangle for yourself. And I'm going to go ahead and I'll call this A again, and this B, and this C, just for consistency. And I'm told this one, sine of B. You know what? What is this one going to be the same as? The cosine of A. Before I even do anything, I know this. I know it. I know it. I know it. How cool. Okay, sorry. This is opposite over hypotenuse. So my reference angle is B. This is where I'm standing right now. Opposite 8, hypotenuse 17 across the 90-degree angle. So let's do the Pythagorean theorem. 8 squared plus BC squared, right? Don't just like plow through it. Pay attention to what you're missing. I'm not missing the hypotenuse. I'm not missing C. 64 plus BC squared equals 289. When we subtract 64, what do we get? 289 minus 64 gives us 225. BC squared equals 225. And when I take the square root of both sides, I get 15. So now I have this side. So now I'm good to go. I've created a picture. So if I figure out the rest of A up here, let's see. The tangent of A, it's here, opposite over adjacent, 15 over 18. The sine of A, opposite over hypotenuse, 15 over 17. Cosine, let's just check it. Adjacent over hypotenuse, 8 over 17. I got it right, yay. And now we're going to change our perspective. Let's go up here. Tangent of B, 8 over 15. It's the reciprocal of the tangent of A. We already have the sine of B. The cosine of B, adjacent over hypotenuse, is 15 over 17. It is the same as the sine of A. So draw yourself a picture. It's really not optional right now as far as the picture goes. We really expect that you are drawing them. So this is I'm gonna briefly, as we finish up, talk about where we're going with this. So here, let's say I want to solve for x. This is different. This is the first time we're seeing an angle, right? This angle that I have is the angle that I'm going to use as my reference angle. I could actually use this one if I wanted, but I want to do it with the information that I'm provided for now. I could figure this out, right? I know that these two are complementary. They add to 90. But let's use this one. So using this angle, I know this side, and that side is the hypotenuse, okay? I'm trying to find this side. So in reference to this angle, this side is what we know as opposite. Well, which ratio sine, cosine, or tangent, it's like a multiple choice thing, would tell us, would we be using if we have opposite and hypotenuse? Sine. Sine is the ratio of opposite over hypotenuse, right? So I could set something up right now that says the sine of 29 degrees equals to the opposite over hypotenuse. And then I've got this equation, which looks different than we've seen in the past because you're looking at sine of an angle, right? But the sine of this angle is this ratio that we just learned about, okay? So that it's important for us to identify which trig ratio, sine, cosine, or tangent, we want to be working with. I'm not going to solve this. You're more than welcome to like play around with it and try and see if you can do it. This is something that we're going to be doing next time in class. So these four, I really would like for you guys to pause the video and just see if you can identify the trig, sine, cosine, or tangent, the function that you're going to use, or you would use to solve for the missing part. Okay, hopefully you've given it a try. So I'm going to pay attention to my angle. Here's the angle that I'm working with. In relation to this angle, this side is the hypotenuse. Be careful, I did this on purpose. Here's my 90-degree angle. Across one is the hypotenuse, even though it's upside down. This side, well, here's my angle that's touching it. This is adjacent. Well, which one involves adjacent and hypotenuse? Cosine. I need to be using cosine. Right? And so I could set something up like cosine of y degrees equals to adjacent 18 over 20. What do we say over here? So let's label the sides. So this side is the hypotenuse. This side is the adjacent. Oh, wow. So I'm using cosine again. Right? And so again, I could set something up like cosine of 18 degrees equals to x over 17. What about this one down here? So here's the angle I'm talking about. This would be opposite. I don't know the hypotenuse. This would be adjacent. So I need to be using tangent. Tangent of 20 degrees equals to 10 over x. And finally, what about this one? Oh shoot, where's my reference angle? What do? We can't find x. Yes, we can. We have the Pythagorean theorem. Right? So I did this on purpose too. It wasn't a mistake. I don't want you to forget what you have learned. Right? So the Pythagorean theorem is so, so, so important to us, and it is so important in trig and things that we do like as we move forward, that I don't want you, like if you have two sides, you don't need anything new. You've got old knowledge to pull on, right? I've got these two sides. I could right now sit here and say 80 squared plus x squared equals 100 squared. I'm not saying why I could, like I am going to do that, right? So use what you know and don't let those things like go away. Like if you can use the Pythagorean theorem, trig is unnecessary. What trig is going to help us do is something like this, right? I only know one side. I can't use the Pythagorean theorem. The Pythagorean theorem needs two sides. So in this lesson, hopefully a lot of this was a review and summary and some extension and explanation of the things that you did in class, as well as a kind of a preview of where we're going with this when we see you during our next live session. So what your job right now is to begin working on Delta Math. Not finish it, but begin working on it. It is really important that you spread it out over the course of the week and see what questions you have so that you're able to utilize office hours and class time to get your questions answered and make sure that you can find success on it. So thank you guys so much for watching, and we will see you all soon.